All right, this is the 4.08 Module 4 review and practice test. So you can use this as a study guide for the test. I'm going to go through and I'm going to take a version of the practice test and work all of the problems. So you can see how those are done, and I will explain how I come to the answer on each one. So let's go look at that now. Okay, so starting out, which of the following best defines 2 to the 2/3 power? Now that's an exponent. That's a 2, and the 2/3 is up here like an exponent. So which one of these is that? Well, if it was just 2 to the second power, that'd be 4. If it was just 2 to the 1/3 power, that would be the cubed root of 2, because a fractional power is a cubed root or square root or fourth root or whatever root. So since this has both, the bottom one tells it's a cube root. The top of the fraction tells us that we square it. So this would be the cubed root of 2 squared, which is the same thing as the cubed root of 4, because 2 squared is 4. So the cube root of 4, right there's our choice. First choice on our practice test there. Okay, which of the following shows the correct steps to find the value of 8 to the 1/3 power? Okay, so 8, we're simplifying down because 8 is the same thing as 2 to the 3rd power, because 2 times 2 times 2 equals 8. So that means it's 2 to the 3rd power is 8. Because that's what an exponent is. It means you multiply it by itself that many times. So this is the same as 2 to the 3rd power to the 1/3 power. So which one of them is doing that? That takes it to 4 to the 3rd power. 4 to the 3rd power does not equal 8, because 4 times 4 times 4 is 64. So that doesn't even equal 8. This has 2 to the 3rd to 1/3. This has 2 to the 4th. Now that'd be like they're saying 2 times 4 is 8, but 2 to the 4th would be putting another 2 out here. And we know that's not going to equal 8. That's going to equal 16. So that doesn't equal it. And this starts out with 16 to the 1/4. I don't even know what that's doing. So this is obviously the answer. We don't even have to go another step, because just looking at the first step, these are totally incorrect because they don't equal the same as the 8. So we can look at that first conversion that they don't equal the 8. 2 to the 3rd does equal the 8. So 2 to the 3rd to the 1/3, and then you take those and you multiply them times each other. When you have an exponent raised to another exponent, that would be 3 times a third, and 3 times a third is just 1. So 2 to the 1st power is just 2. So this just equals 2 when we get to the final number. But all we had to know was which one of these had the right step. So let's move on. Simplify the square root of 3 times the 5th root of 3. So that means this is 3 to the 1/2 power. That's the same thing as 3 square root of 3. And this is being multiplied times 3 to the 1/5 power. When there's not a number outside here, it's assumed that it's a 2. It's a square root. It's a 2. If there's nothing there, it's a 2. So 1/2 times 1/5. So in our earlier lessons, when we had exponents, we learned that when you multiply 2 exponents together, we keep the base and we add these together. So 1/2 plus 1/5. When you add fractions, you have to have a common denominator. Common denominator of 2 and 5. We'll just multiply them together, and they'll be tenths. 2 times 5 is 10, so they'll both be tenths. So since this was a 2 and it needed to be a 10, we had to multiply it by 5. So we have to multiply that by 5. So 5/10 is the same fraction as 1/2, because we're not changing the value. We're just rewriting it. And 1/5 would be what with this? We had to multiply 5 by 2, so we had to multiply 1 by 2. So 2/10 is the same fraction as 1/5. So adding 1/2 plus 1/5 are 5/10 plus 2/10 equals 7/10. Right, so this would be 3 to the 7/10 power, which is our choice right there. So when you multiply two numbers exponent, if they have the same base, we keep that base, and multiplying, we add the exponents together. So we had to add two fractions together on that one. Which of the following is equal to the square root of the cubed root of 6? So the cubed root of 6 we rewrite as 6 to the 1/3. That's what's underneath. That's what's underneath the radical. I'm going to highlight that. That is this part of it. Okay, that's what we're taking the square root of, which is 6 to the 1/3 if we rewrite that. And then all of that is being taken to the 1/2 power. Now this is an exponent being taken to an exponent. This is not multiplying two together. This is taking this one and raising it to an exponent. In that case, we keep the base and we multiply those together times 1/2. So when you multiply fractions, you just multiply straight across. 1 times 1 is 1. 3 times 2 is 6. So this is 6 to the 1/6 power, which is our first choice right there. 6 to the 1/6 power. All right. So see the difference? Remember with exponents, if we're multiplying two numbers together that both have exponents, same number, or if we take an exponent and raise it to an exponent, we treat those differently. So we're combining all this together here, our rationals with our exponents. All right, so what is the exact value? And if you can see that, that's the square root of 180 minus the square root of 125 plus the square root of 5, and simplify if possible. Okay, if we're going to add these together, we want to get them to where we're adding together the same rational, the same number underneath the rational, under the radical. I keep saying rational. I'm sorry, it's radical. Under the radical. These all can be turned into something times the square root of 5. So let's look at square root of 180. That is the same as the square root of 5 times, and we can look at that because if we divide 180 by 5, we know it goes into 180 because it ends in 0. Anything that ends in a 5 or a 0 has, it's a multiple of 5. So 180 divided by 5 is 36. So this is the same thing as square root of 5 times 36. And if you have two things being multiplied underneath the radical, you can separate them. Square root of 5 times the square root of 36. And the square root of 36 equals 6, because 6 times 6 is 36. So this is the same thing as 6 times, not the square root of 6. 6 times the square root of 5. So that equals 6 times the square root of 5. So we can change this to be 6 times the square root of 5 minus something. We need to convert the square root of 125. That's the same as 5 times what? So our 125 divided by 5 is 25. So that's the same as the square root of 5 times the square root of 25. We can just separate the radicals. And the square root of 25 is 5, right? Because 5 times 5 is 25. So the square root of 25 goes backwards to 5. So this is 5 times the square root of 5. So this is 5 square roots of 5. So we have 6 square roots of 5 minus 5 square roots of 5 plus a square root of 5. And so since there's no number up, this is just like 1 plus 1 square root of 5. So if we have 6 square roots of 5 and we're subtracting 5 square roots of 5, that just leaves a square root of 5. There's just one left. We subtracted 5 of them. And then we're going to add another one. So a square root of 5 plus a square root of 5 is 2 square roots of 5. We have 2 of them left over. That would be right there, 2 square roots of 5. So that's what that ends up being. All right. And if you get lost, you can always rewind the video or email me and say, can we get together and you explain that again? Because I'm not getting that. Okay, an expression is shown below. So here's the expression shown below. The square root of 18 plus the square root of 2. And they want to know which one is true. So it's rational equal to 3. It's rational equal to 4. It's irrational equal to 3 square roots of 2, or irrational equal to 4 square roots of 2. So we have to solve that then. So again, we want to get them in the same thing. We want to give them a square root of 2 because there's a 2 in 18, right? So the square root of 18 is the same thing as the square root of 2 times 9. 2 times 9 is 18, which is the same as the square root of 2 times the square root of 9, just like we did in the last problem. What's the square root of 9? What multiplied by itself is 9? So that's 3. So 3 square roots of 2. If you're having trouble breaking that out, you can also break it out as the square root of 2 times the square root of 3 times the square root of 3, right? Because 3 times 3 is 9. And I always say, if you're trying to figure out how to simplify that, there's 2 3's. So if you have a buddy, you got to go outside the house. So the 3 gets to come out by itself. It doesn't have to stay into the radical because it's got a buddy. So it's got a buddy. It gets to come outside. This doesn't have a buddy. It has to stay underneath the radical. It's 3 square roots of 2. So we have 3 square roots of 2 plus another square root of 2. So that must be equal to 4 square roots of 2. It's an irrational answer. It'd be rational if it didn't have the radical. The radical makes it irrational. Okay, when it's simplified down and there's still a radical, it's an irrational number. All right, which of the following is the equivalent function to the function below? And here's our function. And what we have is f of x equals 40. So that's like our beginning amount. And this is like an exponential growth, 1.04 raised to the power of 4x. Now, when we have this number outside here with the variable, we can go ahead and simplify it by putting that inside. It's the same thing as 1.04 to the 4th power to the x power. Because remember, if we have an exponent to an exponent, you multiply them together, you get 4x. We're just breaking it out. Since this is an actual number, we can put it inside and simplify that. So that would be f of x equals 40 times what? So let's put our calculator here. And we will take that 1.04 and raise it to the 4th power. Okay, on the calculator, this is the exponent. So it shows that caret, that's a caret, raise it to the 4th power. And that equals 1.16985. It looks like they went 4 decimals. So if we round that, it'd be 1.169. And since that's a 5, this 8's going to round up. So we just simplified that by go ahead and bringing the 4 and doing the math for the 4. And so that is the same as apparently that one right there. That's our answer, 1.699. 1.1699 is what that turned into. So that is number 7. Let's look at the next one. Okay, the function f of x equals 800 times 1.09 to the 3x shows the growth due to interest that Jim earns on an investment. So here's the steps to calculate an equivalent function. Basically what we just did in the last problem, but they're putting out the steps. And let's see what our questions could be so we know what to pay attention to. Which of the following is the first incorrect step? So somewhere they've made a mistake here, and we're supposed to spot that. Okay, so here's what they did first. Is they took the original function and they wrote it here, step 1. Okay, everything's good. Now, step 2, they took that 3 and brought it inside, since it's a number, just like we did on the last problem. 1.09 to the 3rd power to the power of x. So then they said we'll take the 1.09 and multiply it by 3, so the 3, and 1.09 times 3 is 3.27 to the x. Did you spot the problem? The problem came right there. If something is being raised to the 3rd power, 1.09 to the 3rd power, that does not mean we multiply it by 3. That means that we take the 1.09 and we multiply it by 1.09 and we multiply it by 1.09. That means multiply by itself 3 times. That's what to the 3rd power means, not multiply it by 3. So step 3 was the first error when they said multiply it by 3. That's not the same thing. All right, let's go to the next one. Zen deposited some money in a savings account, and the graph below shows the value of his account, his investment, Y. So his investment is Y in dollars after X months. So the X is how many months? And it asks us, what does the Y-intercept of the graph represent? So that's the y-intercept right there at 1,000. So 1,000 is the y-intercept. Is that the rate of interest? Is that the final value? Is that the total number of months? Or is that him deposited? Well, since this is right here at 0 on the x, 0 months, that is how much he deposited when he opened the savings account. That's his starting amount. And then this shows as he gains interest throughout the months. All right. Let's go to the next one. Okay. So Jake forgot to replace the cap on a bottle of deodorant. And it says it began to evaporate at the rate of 12% per day. All right. So if the original amount of deodorant in the bottle is 30 grams, I'm going to highlight that. 30 grams is 12% per day. Which of the following best represent the amount of deodorant, f of x, that would remain in the bottle after x days? So f of x is the amount. That would be the y. And days is the x. Okay. Days. Amount is f of x. Okay. So let's look at our options. They gave us 4 different graphs here. Let me put them side by side. Okay. Which of the following best represents it? Well, the easiest way to look at that is what did it start with? The original amount. 30 grams. Which one of these graphs has an original amount that starts at 30 grams before it starts evaporating?
That seems awful.
50,
At this point.
4, 40, 30. That's the only graph that starts with 30 grams on day 0. It's the only one that starts at day 0. So that has to be the answer. This is kind of a troubling problem because if he left the cap off his deodorant, he didn't apparently pick it up again and use it for a long time. So I don't know if I'm going to hang out with Jake anytime soon. Jake should have discovered that cap was off at least the next day, 2 days at the very latest, right? Come on now. How long is he going without picking up his deodorant again? Okay, the number of users of the internet in a town increased by a factor of 1.01 every year. So it's growing. If this is larger than 1, it's growing from the year 2000 to 2010. So this shows the number of internet users. F of x is the internet users. X is the years. F of x equals 3,000 times 1.01 to the x power. So the 3,000 is the starting value before there's any years. So that must be the year 2000.
That just means that
year 2000.
And you can get some good grades on it.
There were 3,000 users. Just so we understand what this is telling us. Okay, and then it grew every year. So which of the following is a reasonable domain? Well, domain, all possible x's, all the x's for this function. So what is it? It looked at the year 2000 and 2010. So would our domain be 2000 to 2010? Would that be all the possible x's? No, because x, we've got to look at where x is in the equation. We're not taking 3,000 times 1.01 to the 2,000th exponent, right? We're not raising it to the power of 2,000. In the first year, we're looking at just years from 2000. So after 1 year from the year 2000, 2 years, 3 years, starting with year 0 would be the year 2000. So we're just looking at 10 years. That number would be from 0 to 10. It's never going to be larger than 10. We're just looking at 0 to 10. It's not all positive integers. It's not 0 to 3,000. Just what all exponents would we be looking at to compare those years. We're only looking at, since x is number of years after 2000, we're only looking at 0 to 10. Remember, domains, all the possible x's for the function. All right, let's look at this. This graph shows 3 functions. Here's g of x. It's right here. Has these hollow circles. Let's see. Here's f of x. It has filled in circles. And here's p of x, which is an exponential. It starts small and it gets bigger and bigger and bigger. Which function has all real numbers as the domain? All right. That means negative infinity to positive infinity. Negative infinity all the way to positive infinity. Everything in between as the domain. Let's see. Well, let's look and see. This one goes from here to here. That's it. All these x's over here are not in this function. as well as all of them this way. None of those. Same with this one. It stops here, it stops here. P of x, the exponential function, this keeps going forever that direction. And it gets closer and closer and closer to y equals 0. It gets closer to the x-axis, but it never touches it. Never. It gets so microscopically small, we can't even measure it, but it never touches. The x-axis is an asymptote. That's a math word. It's a math-only word. That's one of the few words that only is used in math and never any other context. Asymptote. On this end, it gets big really fast. But as it keeps getting bigger, it keeps moving right. So it'll get big and big and big, and it'll keep going to all these values of x's. It'll just keep going up really fast, but it does continue all the way to infinity. So this goes to negative infinity this way, and this goes to infinity this way, but it just goes very slowly to the right because it's going up really big. So only P of x has a domain that goes from negative infinity to infinity. All real numbers. That's it. Only P of x. All right, let's move on. Number 13. Jack invested some money in a bank at a fixed rate of interest compounded annually. And here's the equation. It shows the value of investment after X years. So X is years. What is the average rate of change of the value of Jack's investment from the third year to the fifth year? So we want the average rate of change. Average rate of change. Okay, so that's our relevant information. So we need to find out what it is in the third year. Where's our starting point for the third year? 1.02. So we just go and we make a 3 substituted for x because x was years. So we're looking at third year. And then we're also going to see what is the fifth year. Same equation. And see what those two equal. So we're going to do that with our calculator. So we'll start with year 3. We'll take 300 times parentheses 1.02 parentheses to the power of, again, this little caret button right here, to the power of 3. Okay, and that says it is 318 and 0.36. Since this is money, we'll go to the 2 decimals. All right, so we've got $318.36. He started with $300. At 3 years later, making 2% interest, he's at $318. What about at 5 years? So 300 times parentheses 1.02 parentheses to the 5th power, and that is 3. I won't put a dollar sign. 331.24 rounds down, 22. All right, so this is what it changed from the third year, 318. That one, so we have to see how much did that go up. So let's subtract. So we have the 331.22 is what he ended up with. Let me get that where it's not reflecting. Minus 318.36. So it went up, it gained $12.86 between year 3 and year 5. Well, that was over 2 years, right? 5 minus 3, 2 years. Up here, it changed by $12.86. So $12.86 over 2 years, so divided by 2. So it changed an average of $6.43 per year. That's the average. It changes that much per year. Right there, our first option. Pardon me, 643 per year is the average. So remember, we're doing average rate of change. That's per every 1, for every 1 year, for every 1 day, for every 1 change in the X value. All right, so a music competition on television had 5 elimination rounds. And after each elimination, only half the contestants were sent to the next round. So here's the number of contestants in each round. Round 1, round 2, round 3, round 4, round 5. Start with 64, end up with 4. It's going each time. It's cutting down, looks like half each time, right? So it's kind of like they're competing against each other and somebody goes home. Compute the average rate of change of f of x from x equals 3 to x equals 5. Okay, so we can just do a rate of change formula since we have the values. At 5, it equals 4. And from that, let's subtract what it was at 3. It was 16 when it was at 3. So here's what it is at 5. Here's what it is at 3. We'll subtract those to see how much it changed. 4 minus 16, it went down 12 over 2 rounds. It went down 12 over 2 rounds, so the average rate of change was -6. 6 contestants. So we can cross out those two immediately. -6, it represents the number of contestants who will reach the final round, or it represents the average rate that the number of contestants decreased. Well, that's how many went home, right? This is how many are left. This is not how many is going to reach the final round. -6 contestants are not going to reach the final round, right? That's just not right. This is the only correct answer from the choices given. Average rate that it decreased. All right, let's move on. The number of members in Joe's Health Club, members is f of x, increased by 25% every year over a period of X years. Again, X is usually time when you have to deal with a problem like that. X is usually the time. So here's the function. F of x equals 15 times 1.25x to the x power. So that must mean he started with 15 people at year 0. We looked at this period of X years. Which graph best represents the function? Okay, this is another one of these problems. Here's our 4 choices. It's printed over 2 pages. So again, the easiest way to look at that, starting out, is how many has the starting value correct? The starting value was there was 15 people at year 0. This one has less than 2. This has 15 people. This has almost no people. And this has almost no people. Has to be this choice. That's the only graph that has a y-intercept of 15. Y-intercept of 15. Why is that the y-intercept? You know, when x equals 0, we're on the y-axis, right? The x is 0. When x becomes 1, we move over here. When x becomes 2, we move here. But at 0, we're on the y-axis, the y-intercept. In this function, I'm going to look at this real quick. 15. What if x equals 0? 1.25 to the 0 power. What is 1.25 to the 0 power? Well, it equals the same thing as 1 to the 0 power, or 4 to the 0 power, or 781 to the 0 power, or -13 to the 0 power. Anything raised to the 0 power equals 1. So this is saying 15 times 1. 15 times 1 is 15. So that's why that is the y-intercept, because this is going to be just times 1. So when x is 0, y is 15. That is the y-intercept. All right, let's move on. Mr. Brock to the 0 power equals 1. All right, the graphs below show 4 functions. A is this one, B is this one coming down, C is this one going up, D is this one. So A, B, C, D, starting from the top to bottom as we go down. Which best shows the function f of x equals 4 times 3 to the -x power to represent a rate at which a radioactive substance decays? All right, it decays. So decays is going to be less of it as we go on. So we know right away these two that are increasing have to be wrong. Have to be wrong. I'm going to cross those off because that would show increasing growth, not decay. Right? So it has to be one of these two that are coming down. Again, the easiest thing to look for first is which one has a y-intercept of 4. This one. So the answer is graph B. Graph B. Don't make these harder than they have to. You don't have to do a lot of calculations here. Look for the y-intercept on a lot of these. The number of subscribers y to a website after t years, so t is years, is shown by the equation below. Y equals 50 times 1.75 to the t. So what conclusion is correct about the number of subscribers? Okay, it started with 50. And what happened? This is, did it increase by 75, decrease by 75%, increase 50, or decrease 50%? So inside the parentheses, we have 1.75. If we have 1.00 inside the parentheses, if that's 1.00, there is no growth and there's no decay. It does not shrink. It does not get bigger. It stays exactly the same. Anytime it is less than 1, it gets smaller. Anytime it is greater than 1, it grows. This is bigger than 1. It's growing. It's increasing. How much bigger is it? 0.75. 0.75 in percentage is 75%. Because 0.75 out of 1 equals 75%. Right, 75%, 0.75, 75%. Grows if it's larger than 1. Shrinks, gets smaller if that number inside there is less than 1. So that's what that one's doing. All right, this table shows a function, represents the sale, FT is the sale in thousands of dollars, of 4 companies in T years. Okay, so T is years. Which of the following companies showed an exponential decay in sale? Decay. All right, decay means it's getting to be less of it, like something that died and it's decaying, it's becoming less, smaller. So decay would be anything less than 1, right? This is 1.05. That's bigger than 1. 0.75 is smaller. 1.2 is bigger than 1. So those can't be it. Smaller than 1, smaller than 1. So that would be B and D have an exponential decay. Those are the only two that are smaller than 1. Next. Okay, the population f of x in millions of state A of a country. So we have 2 different countries represented here. State A is right here. And this is state B on this graph. After X number of years. So X is the years right here. Okay, and the population in millions is this number, right? And this value. So, which conclusion is correct about the population of state A and state B? The original population of state B was half of the original population of A, or the population of A was half the original population of B. What was the original population? This is 2, 4, 6, 8. So this was 2. That was the original, which it says in millions. So the original population of B was 2 million. What about this one? Oh, our y-intercept is 2. It also is 2 million. So neither one of them was larger or smaller than the other. We can cross out the first 2 options. So the original population of state A was equal, or it was 1/4. It was equal. They were both have the same starting amount, 2, which is in millions. So the original starting y-intercept is the same on both equations. See, we didn't have to do all those calculations with that. We just have to look at what is the question asking. All right, Henry's taking medicine for a common cold. The table below shows the amount of medicine that was present in his body after a certain amount of time, T. Time. All right, so this is the amount that's in his body. After you take a pill, it slowly dissipates. That's why you got to take another pill later. So Greg, okay, so here's Henry up here. That's Henry's information. And Greg's information is down here. So we got Greg down here. He was given 200 milligrams of the same medicine. And the amount of medicine in his body after time is shown by this equation. So we have this table and this equation. All right, so here's Greg right here, which best describes the rate at which their body eliminated the medicine. So the rate. So we know in Greg, it's going 0.88 left after each hour, which means he's losing, 1. If it was 1, it'd be stays the same amount in his body. But he's only got 0.88 left after the first period of time. It didn't say hours right there at the first hour. So if he still got 8 left, he's losing 12 or 12%, 0.12 or 12% each hour. That's how much is being absorbed by his body. All right, and this one, after 1 hour, he has 282. We don't know what the starting amount was, but it was obviously higher than 282. After another hour, it goes down to 265. So we need to figure out what percentage is that, 265.08. It was 282 the hour before. So let's pull out our trusty calculator and say 265.08 divided by 282 is 0.94. He's got 0.94 left, which means if you subtract that from 1, he's losing 6%. All right, so he's absorbing 6%. He's losing 6% per hour. So he's eliminating 12%. He's eliminating 6%. This is Henry, 6%. Henry eliminated the antibiotic faster? No, because he's still got more left in his body. He's got 0.94, where he's only got 0.88. Henry's eliminated at the same rate? No. Henry eliminated the antibiotic in half the rate. Yeah, 6 is half of 12. And the other one says 1/4 the rate. So he eliminated it at half the rate at which Greg eliminated the antibiotic. Fabulous. Let's look at number 21. The price of bronze has increased by 10% per year from the year 2000. So in the year 2000, Harry bought a bronze medal for $120. Which of the following functions can be used to represent the price of it X number of years? So he just wants to know how many years in the future, if it's going up 10% per year, how much is it worth some years down the road? All right, so we can either have 120 or 10 as our initial value. What was the initial value? How much was it when he got it? 120, so it has to be 120, which means immediately we can eliminate 2 choices. Oh, I like it when we can do that. What else do we know? It increased by 10% per year. So this one says 0.9, this one says 1.1. What's the key word? Increase, because both of these are these are 10%. This is 0.1 from being the same. This is 0.1 from being the same, but this one goes down, this one goes up. Increase. This is larger than 1, so it's an increase. Greater than 1 has to be this one. This one's decay. That one's less than 1. The value is going down each time. There you go. So that is number 21. We are well over halfway. All right. We are done with 21. We are ready to move on. Let's look at number 22. All right. The average annual salary of employees in the company in the year 2005 was $70,000. So it increased by the same factor every year. And in 2006, it was 82,000. So there's 2005, 2006. We're from 70 to 82. Let f of x represent the average annual salary in thousands, X years since 2005. So which best represents the relationship between X and FX? All right, so f of X equals, it's either 70 or 82. Which one does it need to be? We had 70 and 82. That's going to be the starting amount, right? So 2005, since 2005 was 70, we can immediately knock 2 answers off our list. So all we need to know, these are both increasing. Was it increasing 1.17, which is a 17% increase? Or was it increasing by 2.2, which that's a double, that's 120% increase. Well, our number sense tells us it didn't go up 220%, but let's go ahead and verify it on the calculator. If we put 82,000 and divide it by 70,000, which was the starting point, that is 17%, 1.17. So that just verifies that this is the correct function for that. But not doubling. It's not going up 2.2. Okay, which statement best describes the effect of replacing the function 2 to the x minus 2 with the function g of x equals 2 to the x plus 5? So if we have 2 to the x minus 2, what happens when that becomes 2 to the x plus 5? What happens when we graph that? Does it shift 7 units to the left, 5 units to the left, 2 units up, 3 units up? Well, x minus 2, if we had a graph, x minus 2, 2 to the x would cross right there at 1. That would be the y-intercept. But the minus 2 is going to shift that 1, 2. It would be over here. The 1 would be over here at x equals 2. Because to get back to here, it'd be 2 minus 2 would put it back at 0. It's going to be over here. So this graph coming down would change over here instead. So if it's plus 5, we'd have to add 5. 2, 3, 4, 5. Negative 5. We had to add 5, negative 5 plus 5 to get back to 0. So that will shift it. If we replace this one with this one, it is going to shift it 7 units to the left. So if it's x minus in the exponent, it's moving it right on the graph. If it's an x plus, it's moving it left on the graph. It's the opposite of what you'd think. Minus moves into positive x's, plus moves into negative x's, because we'd have to subtract 2 to get back to where we started. Or we'd have to add 5 to get back where we started. So that is a shift 7 units to the left. All right, let's look at this. The graph of f of x equals 2 of x plus 4 shifts, let's see, x plus 4, and it will shift 5 units to the right when it's 2 to the x minus k. What is the value of k? So 2 to the x plus 4, right? So that's going to be from 0. It's going to be over here at negative 4, where it crosses at the 1. And if we're going to shift that to the right, 1, 2, 3, 4, 5, we're going to shift it over here to 1. That would be 2 to the x minus 1. So 2 to the x minus k, k must equal 1. There. So we just take the plus 4 and we got to go, if we want to go to the right, that's subtracting. Subtract 5 from 4, be minus 1. And since we already have a minus in our equation, we just need the 1, minus 1. All right. Number 25. Scott and Harry went cycling every day. They increased the number of minutes cycling every week as described below. So Scott, here's what Scott did. Okay, so we'll mark Scott and mark Harry separately. He cycled for 10 minutes every day the first week. 10, and then 15, and then 20, and then 25 in the fourth week. Harry went 10, and then 20, and then 40, and then 80. All right. So if you were doing a table for week 1, 2, 3, and 4, all right, and we look at Scott and Harry. Scott went 10, 15, 20, 25, where this one, Harry went 10, 20, 40, and 80. So which best describes the methods to increase the time? It says Scott's is linear because the number of minutes increased by an equal number every week. Scott plus 5. 10 to 15 is plus 5. Plus 5 again is 20. Plus 5 again is 25. Okay, so that went up plus 5 every time. This one went 10 to 20 to 40. So it looks like it's doubling times 2. 10 times 2 is 20. 20 times 2 is 40. 40 times 2 is 8. So that's going by an equal factor of 2. That's going times 2. So this goes by an equal amount. This goes by an equal factor. This says Harry's method is linear because the number of minutes increased by an equal factor. It did increase by an equal factor. Does that make that linear? If we graph that, is it a straight line? If we graph this, is that a straight line? This is both Harry and Scott's methods exponential because it increased by an equal factor, or both of them are exponential because they increased by an equal number. Well, they don't both increase by a factor or both by a number. One does a factor, one does a number. If it's a factor like that, that is exponential. If it's going times 2 or something like that. If it's just a plus the same amount, that is linear. So Scott's method is linear. Harry's is not. It is exponential. So that answer is wrong. And then they were not both exponential because Scott was linear. So these answers are not correct. All right, let's move up here. The sales total at Robert's Food Store have increased linearly. That's a fun word, linearly over the months. If someone likes to write tongue twisters, write one with linearly. Which of these best shows the sales in the first 3 months? Linearly. 1,200, then 1,212, then 1,224, 12. 1,200, 1,236, 1,273, 08, 1,200, 1,285, 48, 1,370, 96, 1,200, 1,224, 28, 1,248, 48. So to be linear, it would need to increase or it could decrease, but in this case, it's increasing. Same amount every time. Every time has to be the same amount, the increase. So every time the X went up 1, which in this case is 1 month, 2 months, 3 months, every time the X goes up 1, the function has to increase the same amount. So how much did it increase here? It increased plus $12. And then over here, it increased plus $12.12. That's not the same. Adding $12 and adding $12.12 is not the same. Not linear. This went up $36 from 12 to 1236. And from 1236 to 1273.08, that went up $37.08. Not the same. Okay. 12 to 1285. So that went up $85.48. And that went to $1370.96. Well, that is also another $85 plus and 48 cents. That looks to be linear. We can double check this last one. This went up 1,200 to 1,224.28 plus 24.28, and then to 1248.48. So that went up plus another $24. And from 28 to 48 is 20 cents. So that did not go up the same each time. That's not linear. So that is our choice, the third one right there. It went up linearly. Okay, the store had 175 cell phones in the month of January. Every month, 10% of the cell phones were sold and 10 new ones were stocked. So which recursive function best represents the number of cell phones in the store, f of n, after n months? All right, let's go back to lesson 406. If you struggle with the series, this is a recursive series, lesson 406. So this says the first one, you have 175, and from that you subtract 0.9. So you have 90% left. 90 times n minus 1. So you're going to take 90% of it and subtract it from the total, and then add 10. Where the f of 0, the beginning amount, f of 0 is always your starting, is 175, and the number of months is greater than 0. So this says subtract 90% of your stock and then add 10. Well, we sold 10%. We didn't sell 90%. We're not subtracting 90%. This says take 10% of f of n minus 1 and add 10. So we're going to keep 10% of whatever we had the previous month and then add 10 to it, because n minus 1 would be the previous month, right? Because n is whatever month we're in now. We're in n month. So anytime we look at n minus 1, that's last month. So if we're in month 2, we look back at month 1 to see what we had left. Okay, so look at last month. We're going to keep 10% of it and add 10. That's not right. We sold 10%. We didn't keep 10%. So this says take 175 and then add 90% of what we had last month and add 10 more. Well, we're not selling anything there. We're adding phones. We start with 175. We add 90% of what we had last month to the 175, and then we add another 10 on top of that. We're going to have a lot of phones and not selling anything. Can't be that either. Let's hope this is it. This says keep 90%, 0.9 times what we had last month. So we're going to have 0.9 times what we had, 90% of what we had last month, and then add 10 to it. Yeah, whatever we had last month, we sold 10% of it. So we keep 90% and add 10. That is our choice. Recursive functions. Again, if you struggle with those, go back to 406. If you don't understand that, get with me. We'll look at those. Okay, Bruce added some chlorine to the water in a pool. It evaporated at a fixed rate every week. Fixed rate. This table shows the amount of chlorine in ounces that was left. So after 1 week, he had 54. After 2 weeks, he had 27, 13 and a half, 6.75. See what this happened? That's half, right? 27 is half of 54. 13 and a half is half. That's our fixed rate. Our fixed rate is a half. That is half. So 0.5 or 1/2. Okay, which function best shows the relationship between the weeks and the number of ounces left in the pool of chlorine? Okay, this says start with 108 and then 1/2 to the n minus 1. Well, if we back this up to 0, week 0, we would start with 108. So the way to do this is the way I like to do this. Let me give you a tip. Let's test it for one of these n's and see if the formula comes up with that. Let's week 2. That's a nice, easy one. Let's make that a 2. And we're going to put that in all of these. We're going to substitute 2 for n. And it says when n is 2, we should have 27 ounces. So let's just, since we have multiple choice, it's easy to just test that. So this would be f of 2 equals 108 times 0.5 to the 2 minus 1, which is the same thing as 1, right? 2 minus 1 is 1 to the first power. So 0.5 to the first power is just 0.5, just 1/2. So 108 times 0.5 is 54. We didn't have 54 left in week 2. That formula doesn't work. How about this one? F of 2 equals 54 times 0.5, or 0.5 is the same as 0.5. I didn't put a 0 in front of that. And this is just to the n, and our n is 2. So let's put that in our calculators, double check. 0.5 to the 2 should be 0.25, but we will put the whole thing in the calculator. Times parentheses 0.5 parentheses squared, the power 2, that equals 13.5. We did not have 13.5 left in week 2. That formula does not work. 108. This is almost the same as that one, but this is n plus 1 instead of minus 1. So f of 2 equals 108 times 0.5 to the n plus 1. N is 2, plus 1 is 3. So 108 times 0.5 to the third power. Okay, 108 times 0.5 to the third power is 13.5 again. Only got one left. This better work. Okay, so f of 2 equals 54 times 0.5 n minus 1. 2 minus 1 to the first power. So 0.5 to the first power is just 0.5. So 54 times 0.5, or times a half, is 27. We're supposed to have 27. That's the only formula that works for 2. So it should work for everything. And if these didn't work for 2, they won't. It doesn't matter. It has to work for every value for it to be a proper function. So process of elimination. Make that your friend on a multiple choice. See how that works. Okay, 29. The amount of radioactive material changes with time. Okay, this shows the amount of radioactive material left after time t. So this is t is hours, and here's the amount of material left. At 0, it's 180. At 1, 90, 1 hour, 90, and 2 hours, 45. So which exponential function best represents the relationship between ft and t? Is it f of t equals 0.5, 180 to the power of t, 180, 0.25 to the power of t, 180, 0.5 to the power of t, 0.5, 50 to the power of t? All right, so what's this number that comes first? That's what we start with, right? And we start with at hour 0, 180. We can instantly throw out two choices. Okay, what happens after 1 hour? We go from 180 to 90. What goes the next hour? 90 to 45. That is 0.5, right? That's or 1/2. We have half of what we had. 0.5 same as 1/2. So that's how much is changing every 1 hour. So we can eliminate that. It has to be this one. 0.5 times the hours. All right, to the raised to the power of the hours, pardon me. Okay, the functions f of x and g of x in the table below show Jane and Mariah's savings respectively in dollars after x days, and there's some values missing. Okay, so this is Jane's savings right here, and this says Mariah's savings right here, which means they have this wrong because they had these backwards. Okay, Jane is g of x, and she had 9 using this formula, 3 to the x power, and this is 3x. This is not 3 to the power of x. This is 3 to the power of x. This is 3 times x plus 3. Okay, so in years, starts with 3 to the power of 1. 3 to the first power is 3. When x is 2, 3 squared is 9. This one, 1. 3 times 1 is 3, plus 3 is 6. 3 times 2 is 6, plus 3 is 9. So in the long run, which statement's true? Well, let's put in the blank and let's see what happens next. 3 to the power of 3. That would be 3 times 3 times 3. It was to the power of 3. 3 times 3 is 9 times another 3 is 27. So this would be 27. 3 times 3 plus 3. 3 times 3 is 9 plus 3, 12. So this is 12. So in the long run, as it continues on, 3, 9, 12, 6, 9, 3, 9, 27, 6, 9, 12. It looks like Jane is going to end up with a lot more money than Mariah. Saving Mariah have more? No. Savings increased by the same? No. Same percentage? No. Jane's is going up faster. Save like Jane. All right. We're approaching the end. I see one page behind this one. We're almost there. The functions f of x and gx are shown below. F of x is 0.05x, where g of x is 0.05 to the power of x, which best describes the graphs. So this says either the graph of g of x will eventually exceed, which means it'll be higher than the graph of f of x, or f of x will eventually exceed the graph of g. Which one's going to end up in the long run? Which one's going to be higher? Or will the graphs both have their y-intercept equal to 1? Well, what is the y-intercept here? With x is 0, the y-intercept is 0, because 0 times 0.5 is 0, so y-intercept equals 0 on that one. So we know that they won't both have it. That we can rule that out. Or both have the y-intercept 0.05. No, because that one's 0. We already calculated that. So one of them is going to be higher than the other. So it means we need to understand what the graph looks like for these two. So f of x equals 0.05x. The slope is 0.05, which means we'll start 0, 0 and go very, very small, slow linear graph, slowly getting bigger. All right, very slowly getting bigger. This is less than 1, so it's decay. It's coming down. It's going to have a y-intercept of 1. But an exponential graph is going to look like this. It's going to come down, And remember, it's got that asymptote. It's never going to touch the x-axis. It's just going to get really, really close the longer it goes. So it looks like that. Since that's below 1, it's coming down like that. If it was greater than 1, it would go up. But this is decay. It's going down. So eventually, see f of x, this is f of x right here. And this is g of x up here. G of x starts out a lot higher, but as it goes, it's going down, down, down. And this one, even though it's going up really, really slow, eventually f of x will exceed the graph of gx. The longer it goes, it will keep going up, and this one's going to keep going down. All right, so let's just understand what those graphs look like. So I put up a Desmos graph on the screen for you so you can see the same thing. There you go. G of x, f of x. All right, let's look on to 32. Okay, the same amount of trash is dumped into a landfill every day. The function below shows the total number of tons of trash. So N is the tons of trash after X days. Okay, N equals 2,000, X plus 1,000. What does that 1,000 represent? Well, this X, number of days, is attached to the 2,000. So however many days there is, we multiply that by 2,000. Well, the only reason we'd multiply the number of days by the 2,000 is that must be the amount that's dumped every day. So every day there's 2,000 tons of trash added to the landfill. So if we go back to the very beginning, if we're on day 0, we're just now starting this to track this, day 0, 2,000 times 0. All right, so if n equals 0, day 0, 2,000 times 0 is 0 plus 1,000. So it must have started with 1,000 tons of garbage already in the landfill before we start tracking this. So that would be the amount of trash originally there before we started adding 2,000 every day. So it's not the rate that increases every day. That would be the 2,000. All right, the last page. And there's only one problem on it. One problem. All right, a ball is dropped from a certain height. The function represents the height, f of n, in feet, to which the ball bounces on the nth bounce. So the n is the number of bounces. What does number 0.7 represent? Oh, good question. Let's see. So that means the ball bounces to 30% of its previous height. So if it was at 100, it dropped to 30, and then it 9 from that. It starts at 9. Is it bouncing to 30%? Is the 0.7 the height at which the ball bounces? At the nth bounce is 0.3 feet. Does the ball bounce to 70% of its previous height with each bounce? Or the height from which it drops is 0.7 feet? Well, this says that we start at 9 feet, and after first bounce, after one bounce, we've got 0.7 of that 9 feet left. So that is right there. The ball is bouncing to 70% of its previous height each bounce. It starts at 9, it bounces, now it's got 0.7 of its previous height. It'll bounce again, it'll have 0.7 of that previous height, and so on and so forth. So there you go. That is the entire practice test. You can go back and look at any of those problems. The test will have similar problems. So if you understand how I work these, you should be able to understand how to work the test problems. So take the practice test for yourself. See if you do well. If you don't, look, just fast forward to the video to find the part where I worked on what you missed, and then review that and do well on the test. So we'll see you guys next time. Do work you can be proud of.